So our next one, what is a theory, kind of hits on a little bit of what I was talking about um, with uh, how a theory differs from a hypothesis and how it kind of comes together. And in the video, you should have seen multiple groups all trying to build the same Lego model. They all had the same phenomenon that they were studying, but they couldn't use direct observation. They had to use indirect observation. They had to touch and feel and experience things, and they then would build a model from that. That's what scientists do, right? They all see this big phenomenon. They're all studying this same phenomenon. They all start developing models to describe it, or hypotheses to explain this real thing that's there, by recreating a model of it or a hypothesis of it. And as they do that, they slowly build models that are similar to each other. And as they build those models, and then we see the consistency in the evidence, that's when we become more confident in the model itself. And that's what a theory is. Okay. All right, this is probably one of the top things I get questions on. Question 10 here, when we start talking about statistics, okay? If we have fair coins and we flip that coin 100 times, we would expect to see the heads and tails to come out to be something near 50-50. It probably wouldn't be exactly 50-50 for most people, but it would be close. And so if we are testing to see if a coin is not a fair coin or not, right? We have a null hypothesis that it is fair, and that we would end up with results that should be close to 50-50. We can use this idea. We're kind of trying to understand how statistics works. You're not going to be tested on anything relating to the statistics, but it is helpful if we can understand, just as everyday citizens, how statistics work. So this is kind of give us a real basic primer in that. So we want to test this coin, but to test it, we need to have some sort of number, a quantifiable data point that lets us compare these things. And so we have to come up with ways of saying, well, how far away are we from the expected 50-50 deviation? And so that's what these things are here for us, to kind of see, okay, well, I could take the absolute value. I could come up with any number of statistics. Ultimately, what we're trying to see is how far do our expected results deviate from our how far do our observed results deviate from our expected results? And so if we used, say, this one with absolute value, right? If we had 49 heads, 51 tails, well, then we would have, so we'd have one here, and then we would have one here. And because it's absolute value, we'd have -1 and then 1. Because it's absolute value, we'd add those together and they become 2. So that would be our score for that observation. And we would have a deviation of 2 from our expected. Now, we want to repeat that trial over and over again. And as we repeat that trial, we get a set number of results. And so that's what this chart is showing us here. This is how far we deviate from 0 as we do multiple trials of this. Now, if we have coin A, coin B, and coin C, and they fall within this range of distributions, that's kind of where we would expect most of our results to be, between that 0 and 10 range, right? That's where the most frequent ones are. But look at D out here. D is all the way out here. This is a really rare result. And if we would say that this result is more extreme than, say, 95% of the results that we might get by random chance, then we'd be confident enough to say that this result is from a coin that is not a fair coin. So we would reject the null hypothesis once we get a result that's this extreme. And so that's kind of the way that we use, in a very basic way, statistics. This is frequency-based statistics. We're saying, how extreme is this result compared to if we did these results, we did this same experiment 1,000 times. And so by doing that, it takes some of the, as much as we can, the subjectivity out, right? Where we say we're only willing to accept our claim that this coin is not fair if the results are more extreme than 95% of the results that we might get if it were a fair coin. And so that really helps us take the subjectivity out of it. Also, as part of this lesson, we had this lecture on evidences and sources. I'm not going to go over all the same ideas because you can watch the video if you want to see that. But I will just kind of review the different types of evidences, right? We had correlational evidence. This is where we've gathered data from multiple variables and we're going to compare those variables, but we don't actually have an experiment set up. We're looking at data and we're trying to see how those two things compare. This is done by scientists all the time. Sometimes it's the only type of evidence that we have, whether because we don't have the money or the time to recreate an experiment, or we simply don't, or to create an experiment, or we simply don't have the ability to do that, or we have ethical problems with that. Like, for example, in that suicide study, right? If we have concerns that altitude is tied to suicide, it would be really unethical to force people to live in certain conditions where their suicide rate might be affected. And so we wouldn't want to do an experimental trial with that, right? And so we're kind of stuck with this correlational study because it's the only thing that's appropriate to do. So correlational studies are, we don't have experimental design in that traditional sense that we've talked about. And we are really just comparing two data sets and see if there is a pattern in those data sets as they relate to each other. The next one we went over was anecdotal evidence. Anecdotal evidence is an experience. And because it's an experience, we might be able to use it as a puzzling observation. We'd probably want us to have multiple observations of that, so it really wouldn't even get us there. But anecdotal evidence serves as that kind of just a personal experience. And we can't really use that in science unless we get multiple personal experiences. And even then, it would just be our observation, right? We'd wait to either get correlational evidence and gather more data that way, or move into causational evidence, which is our third type. Causational evidence is when the scientist has control. They have a laboratory setting as best they can. They're controlling those variables. They're changing a variable on purpose, maybe doing multiple experiments and changing multiple variables, but they're deliberately impacting the independent variable. They're measuring things as a dependent variable to get results. And it's very much all about getting to that cause and effect, right? We talked about randomized control designs and things like that, where we're setting up conditions, we're randomly assigning groups to those conditions, and then we're measuring results from that. That is going to be what lets us get to causational evidence. And so those are some of the key characteristics that are different. One other thing that's really key is both correlational evidence and causational evidence will go through something called peer review, where other experts in the field will examine the methods, the practices that were done in the experimental study, the statistical analyses that were done in the studies, and they will say, yes, this was appropriately done. We support that this paper deserves the attention of the scientific community. They aren't necessarily saying they agree with the results, but they are saying, or they necessarily agree with everything the authors are saying. They are saying that the authors are appropriately stating their evidence, and they conducted an appropriate experiment or data collection. And so peer review is a key part of that. So we want both correlational and causational evidence to be peer reviewed. The last part of this lesson was the sources. We have sources, we have primary sources and secondary sources of evidence. For primary sources, that's going to be what we saw for in the altitude study and then with Dr. Johnson's guppies. In that type of study, what we're seeing is these scientists themselves are writing the document. They're describing the things that they've done. It's actually a very technical document. They are reporting their own things. It's hyper-focused. It's focused on one particular thing. That's going to be primary evidence. That's very different than what you might have seen in like history, where it's somebody's experience in a battle or something like that would be primary evidence. We don't use those terms the same. They're different. Secondary evidence is when someone has taken a look at these big ideas and they try and synthesize them and then communicate them to a more general audience. So primary evidence is about pushing the boundaries of what we know. Primary sources. Secondary sources are about describing what we have a lot of evidence for and a strong understanding of. And so they're kind of a different thing. Textbooks are the classic example of a secondary source. But and the secondary source might be peer reviewed, but it's not going to be the scientists themselves breaking down in a technical way what they had done in their experiment and how they analyzed their data. So it's a different approach, different goals, right? And they each have their strengths and weaknesses.